micro-air cycle system.
Hello, I'm Aaron Harden. These are my teammates, Matt Tiso, Inting Chu, and Bill Mao. We did the MAX system, or micro-air cycle system. What this is a revolutionary air conditioning idea. We're going to take all of those clunky components you see in a modern air conditioning and combine them all into one micro-scale device. Now what the MAX device is essentially two copper plates about 100 micrometers apart. That's about the width of the human hair. When we compress these plates, we heat up the air inside, and we'll use a heat sink to extract the heat from it. And then when we open the device, it will release cool air. As you can see, our objectives started with an analysis. Matt did a very good job of combining a lot of different sources, including talking to physics teachers or talking to people in industry, and made a really great document that we use for a lot of things. These two charts up here are actually from his document. We also had a fixed seal, which is a MAX device inside of a closed chamber, which is isolated from the outside environment. And Bill did a lot of work on that, just building the devices and then testing them. And Inting built us some software, it was a VI, that we used to measure the heat inside of the chamber. We put a thermocouple inside of the device, and then measured the voltage across the thermocouple to figure out what the heat was inside of it, so that we could really analyze our device from a heat standpoint. We also wanted to do dynamic seal, which is a MAX device that has an interlocking gasket so that the seal is created as the device compresses. I did work myself on that in theory and also in testing, and Rebecca Toll from the physics department built these devices for us. We also did a lot of research for the future. We wanted to be prepared for next semester, so we did some research into materials we can use to enhance our device, particularly insulators, so that we can keep the heat inside the chamber longer, so that whenever we attach a heat sink, that will be the only thing removing heat from our system to increase the efficiency. We also plan to design a control circuit to really enhance the properties of this system by controlling it in the way that we want, now that we've characterized its properties. As you can see, we had kind of a progression of geometries as we started from a closed chamber with no device in it, just to make sure that our theory is correct. And then we progressed to a closed seal chamber. And then this is a drawing of our dynamic seal. I know it's a little hard to see, but it has the interlocking gasket. And we actually made some of these devices, and we got a 3-degree temperature change on the dynamic seal. That's what this graph is down here. In conclusion, we did a lot of work this semester really characterizing a two-vane setup. And next semester, we are going to build a full system and characterize the heat properties of that system. I'd like to open it up for questions now.
What do you mean it's sharp? So there have been other projects on micro air handler. How did this improve on the previous design?
So in particular, we wanted to analyze the heat properties of the system. A lot of work has been spent on analyzing just different properties of the system, but we want to make sure that we can generate a heat delta and that we can extract that heat and thus cool the inside. Because if we can't transfer heat, then there's not really much of a project there.
So this sounds like a mechanical engineering project to me. Did you, do you or your team members, have you taken any of the core courses in ME on heat transfer, or I guess fluid mechanics would be appropriate, thermo? And if not, how did you build up your expertise to be able to tackle this project?
So we had to learn a lot for this project because we aren't physicists, but I mean, electricity is part of physics. We have had to learn some physics, and heat does have a lot of the same properties as electrical systems, you know, flowing out, conductivity, those kind of same parameters. So we did have to learn a lot for this. It is, in a lot of ways, a mechanical engineering project, but we really just devoted ourselves to it and to really learning this stuff and characterizing the device. So just lots of different sources. We all had our different places in this project and made it happen.
Thank you very much.